So, all right. So, DNS is something that we've all sort of taken for granted, but functionally speaking, DNS is what and who you are on the internet. If you don't have functional DNS, you pretty much have nothing working. You have no email, you have no web services, you can't offer any form of service to your customers or clients on the internet. Getting robust DNS that works and cannot be taken out has even gotten to the stage where upper management now sees that as something that costs them money. The plus side of this is we are no longer working very hard to justify keeping our DNS infrastructure up and running. What has made life more complicated is that not only is it the way that we are seen now on the internet, but bad guys are both coming in and attacking our DNS, trying to take it out to effectively take us off the internet, but they are also using it to further their other evil aims in terms of attacks or communication for their own infrastructure. So what I'll be talking about are some of the things that happen with DNS that can corrupt the DNS that you have and how they are using it against you, and some of the things that you can do to try and defend against that. So one of the first things that started getting attention was caching servers. Large internet providers who have one set of caching servers or a cluster of servers became a very rich target. You could take over someone else's DNS without actually subverting them by subverting someone else's cache. So real quick on how the recursion works, basically when you make your request, it goes out to the root server, you go through, and the recursive server will go through all the various servers it needs to finally return that answer back. This is how you get to this particular website, whatever. So what you're usually going to see is some kind of stub resolver. This may be your operating system. More common these days is your resolver itself actually has a stub resolver built into the code that does its own choices, doesn't even bother to necessarily talk to your operating system to do so. Name servers themselves, when you do talk to some other name server, it will then go out and make non-recursive queries in order to go through. Who offers that? Who does that recursion for you? It could be your recursive server. Some auth servers will also do recursion, though that's usually not recommended. It's another sort of mitigation risk. If your cache is corrupted or your recursive server is in some way vulnerable to something, that could also take out your own authoritative zone. So you've just given yourself sort of another place that you have to defend. Forwarders are another fairly common technique. Usually they'll be put on the outside of a firewall, and all of the clients in the enterprise will use those. So forwarders may do recursion as well. You may even have your own internal servers doing some of it. So cache poisoning is getting to that recursive server and essentially getting it to put data that is not correct, that is not what the authoritative zone has. You know, instead of my bank, I get to the bad guy's website or use their DNS that lies about who my bank is. And there are a number of reasons why that's been happening. The biggest reasons basically broke down to flaws in most of the big name server code. Most of the bind related and unbound code are probably what most of the world uses, other than, and Microsoft was certainly not immune to that as well. One of the other things was simply flaws in the DNS protocol, and we'll talk about DNS message sizes as well. One of the other things that it was not at all uncommon 5 years ago or 10 years ago that we've tried to discourage is open recursive servers. That means that it will take a query from anyone with no qualification and perform recursion for them. Unfortunately, for very large ISPs who are running recursive servers for their customers and people like Google, you may wind up having to run what is effectively an open server. But if you don't have to, that's one risk that you can get rid of fairly quickly. So I've poisoned the cache. I'm the bad guy. I've done something. What does that really allow me to do? Well, allow me to do all sorts of things. I can have you put in bogus records. So instead of www.wellsfargo.com pointing to an actual Wells Fargo server, I can point you to someplace else that looks and smells like Wells Fargo and possibly gets information from you like your login and password. So I might reveal something sensitive. It might mimic my corporate login and get my login and password, and suddenly I've got credentials that get me into your corporate data. And it might just get you to a wrong place. They may decide that that's one fun way to hack you. You know, it was fairly common for Anonymous to take out various government sites to show that they could effectively take you off the internet. And one of the things they would do is they would insert bogus data and point you to their website with their content saying whatever they wanted about the people they didn't like. Pretty much anything where you could do a man-in-the-middle attack in security, where you are between what should be the ultimate source and the user, and play games with any of the traffic in transit between them. So one of the first cache poisoning attacks, Cache4Off figured out that there's a way, because of the way Bind, one of the larger open source resolvers, work, you could actually fool it. So the bad guy would set up alternic.net as a name server. He controls that name server so he can put whatever data he wants into it. He then goes off to this open recursive server and says, hey, can I get the A record for something in that domain? And that recursive server is going to go back and it's going to ask what it thinks is the authoritative server, and it is. But what happens is you don't just get the legitimate record. I also stick in an A record for a zone I have no direct access to, and I'm not authoritative for. But I stick it in the additional data section, because when you have a DNS query, you have the query, you have the actual response with what you asked for, and the name server can give you additional data to make life easier. It's supposed to be for things like glue records, so when you say, I'm not authoritative for google.com, I only know about .com, but here are Google servers, and if you don't know the A record to get to those NS records because they are in the google.com domain, I'll give you those A records to make your life easier. Well, they didn't really check what was coming in additional processing. So what you wound up with was he would stick that internic.com record right into the cache, and the next time somebody asked for it, he wouldn't actually go out to internic.net. He would simply check his cache first. And of course, the bad guys would put in a TTL of how long you keep that record in cache of weeks at a time. So until you reboot that server or flush that cache manually, once I've accepted that bad data, I'm serving that to every one of my customers until that goes away. And the basic technique also that has to do with this is there's supposed to be a message ID. When I send out a query, the response I get back is supposed to have the same message ID, so I know this is the answer to this particular question. And it's supposed to be a random 6-bit quantity. Notice I said supposed to be. So the question, of course, was how random was it? Well, what another researcher had discovered was that the prime number generator that Bind was using was not good code. It was not really a good random number generator. So the pseudo-random that it had was not even pseudo. Basically, you always knew that if that message the ID was even, that you had already eliminated the next possible to 1 of 10. So you had a 1 in 10 chance of just guessing it. And basically, after some number of queries, you could pretty much guess where in the seeding sequence, because what happened was it wasn't really pseudo. It started from a semi-random place, but once it started from there, it was a very predictable algorithm. So once you got about a dozen queries in, you actually knew where they had seeded from, and forever thereafter, basically you ran the same code and could always match. So the theory was that you had to guess that message ID to get that message in there. But the reality was that if you went through a few rounds first before you tried your first poisoning attack, you actually could pretty much guess correctly, and therefore you could get that message ID correctly. And some math that I won't dive into here, it's in the slides, but basically it's a birthday attack, i.e. it's the same problem as how likely is it for two people to have the same birthday in some sample size. And what it boils down to is it seems like that's a very hard thing. You know, any two people in the world, except there's only 365 days and it shrinks very quickly. And so once you get above 50 people, the odds are really, really good that you will have two people with that same birthday. And similarly, what happened was, even though in theory that 16-bit message ID was random, in reality, once you had a certain number of those in, which for a computer spitting out 600 UDP packets these days over a fat link takes very little time and effort, you're pretty certain to get it. So what this essentially said was also you could go through and I will make a query some random thing that I know doesn't exist. I will use a random label at paypal.com. That means I know that this name server doesn't yet have that in cache because no one would have asked for it. That means I know he's going to be going off to PayPal. Well, and now's my chance. What I then do is I sit there, and since I know that I have a 90+% chance by flooding out 600 messages, I just throw out 600 messages, and if I have a fast link, there's some reasonable chance that one of mine will get there and hit correctly before the actual correct response comes back from the real PayPal servers. And it may not work the first time, but because of the fact that I'm also using a random label, I can do that over and over again. And the only way you can notice that someone is doing this is if you somehow knew that PayPal.com was the target and you had something intelligent enough to figure out that those labels were random. So very hard to catch until, of course, it got poisoned. And then again, what they do is they send that record, and in that additional processing section, I happily take that, and at the time, bind and unbound would both just stick that in cache, and you're done. So there were some attempts to prevent some of this. The reality was that at the time DNSSEC was not anywhere near where it needed to be. Key rollover was still a problem that most people dealt with. The root was not yet signed. It was unclear if the root was ever going to get signed. And even things like DLV, sort of a look aside so that you can look somewhere else if you can't find the root to start your chain anchor, it wasn't looking promising. So what folks did was they did improve that randomness such that it wasn't just the birthday attack, that you really actually got back to having 64K of possible random messages as opposed to a few hundred. Because it's much harder to get 64,000 spoofed responses back before the authoritative server can answer than 500 or 600. And before this, bind and unbound always used the same source port address for all of their queries because it's this little tuple which is included. So they said, well, if we simply randomize the source address, or sorry, source port as well, that gives us another bit of randomness that they have to go to in order to be able to forge this, because I have to respond back to the same port that sent out the query. But again, okay, so fine, it gives us something, and it's certainly an improvement, but you can still spoof. And another researcher proved that basically, and this was high-speed LAN in the parlance of 3 to 4 years ago, i.e., I think a 1 megabit connection was considered high speed. So these days where you can get 20 to 100 megabits in some places, and CPUs and clustered PCs have gotten even faster, this is probably under an hour. So, okay, we all see that obviously it's bad to have our cache poisoned. So what can we do, and what have we done? Well, we have increased the randomness and the quality of the random number generators for message IDs for source ports. Even more importantly, Bind and Unbound started doing sanity checks. They would put stuff into glue, but they would mark it as, I got this as additional processing, I haven't actually validated it. So before they start reserving it, they would actually make some check of the authoritative server. And anything that comes from the authoritative server has more precedence than anything that just came in glue. The best solution is DNSSEC, and these days it is not nearly the daunting prospect that it used to be to get DNSSEC up and running on your system. So that's dealing with the cache. But obviously one of the other things that you need to worry about is your own authoritative server that run any of your zones for business. You need to make sure that those are up, running, available, and performing well. Because one of the other things that was learned very long time ago, users will switch or reload or go to a different website. I believe the number still is after 250 milliseconds of waiting. A quarter of a second, things won't load, they will hit refresh. And if they don't get it after 1 or 2 tries, they will usually just move on and stop trying to get to a site. And that's from the moment that their stub resolver in their browser starts the first DNS query to get to the first thing, loading the HTML, getting whatever subsequent pages, all of the other stuff that web designers love to shove down their throats, and all of that, and all of those having DNS lookups, all working in 250 milliseconds. So obviously, if your first round authoritative DNS response takes 200 milliseconds or 300 milliseconds, they haven't even started loading the initial HTML or CSS or anything they need to get your page down. So one of the ways that bad guys will take you out is very simple. Just sheer volumes of crap going down your internet pipe. Botnets these days, average size is 20,000 infected machines across multiple ASs, across multiple regions, all sending you bits that hurt. And they are prevalent. As you can see from the numbers, pretty much any ISP is going to see some form of denial of service attack against one of their customers pretty much all the time, and anyone of any reasonable size is going to see hundreds of these things, dozens of these attacks a day, and gigabits of data flowing over these pipes. And most of us do not have gigabits of bandwidth. Hopefully all of you have your DNS at co-location facilities that have fatter pipes, and you're not sticking it down in corporate headquarters at the end of a skinny pipe, but not all of us necessarily have the luxury of placing it exactly where we want. One of the other things that they are doing is they're being very intelligent now with the use of their botnets to make it even more painful and effective. They're using very high yield results. If I ask for a DNSSEC, like I asked for the RR6, you signed your zones, you may have a reply to me that's 500 bytes or 1K very easily. Might be even more depending on how big it is. Well, I can send you a 30 or 40 or 60 byte UDP packet once and force you to shovel 1K back up your own pipe. And if you're using DNSSEC and you're using NSEC 3, not only do you have to have all of that bandwidth, but if they go for non-existent labels in NSEC, you have to prove non-existence, which means you have to do prime number factorings to create the 2 records that bracket that non-existent record to prove that that record isn't in your zone and authoritatively prove it. So every single one of those queries not only shoves hundreds of bytes potentially up your pipe, but it whacks directly in CPU and prime number factoring, slowing down the web server itself. And all of that, again, for a 60 or 80 byte packet on their case. And so imagine 20,000 of these machines all over the place across multiple different paths with different source addresses or forged source addresses, all sending a little bitty packet that forces you to beat your CPU to death and clog your own upstream bandwidth. So, what do? Well, if they aren't smart, and fortunately for us, many of these guys are not terribly clever, A lot of them are little script kiddies that got this cute little toolkit from some other high school student that they know. So some of them may actually be coming behind certain paths and certain prefix lengths that you can actually use in an ACLN filter. Or the attack is persistent for long enough across one address range that you, or possibly even your ISP or upstream transit provider, may be able to filter. Obviously, higher capacity servers. There are a number of folks that have optimized servers with specialized hardware. It's not commodity x86 box with a Linux operating system and open source. They are able to deal with, in some cases, hundreds of thousands to 1 million queries per second of normal traffic. So suddenly you've raised the bar that 20,000 of these bots are actually going to have to sweat to get you enough DNS queries in a second to actually make you sweat doing resolution. And of course, clusters or load balance servers where you have multiple machines all going through. Certainly for things like NSEC 3, that will help because at least you're spreading the pain across 3 or 4 machines to calculate all of this. You can, of course, put more authoritative servers out in different places up to a point. The up to a point is because there are some performance issues, obviously. One of them is that most of the time you want all of your NSs to fit into one 512 packet, so you do not have to do EDNS 0 or TCP to be able to tell someone what your NS servers are. A lot of clients don't handle having multiple NSs or multiple A's or other things well. So you can do it 6, 8, 10. Once you get up to about 12 name servers of actual records that are publicly visible, you're not going to get much benefit. Then you start doing things like Anycast, where you can use the internet and BGP and route aggregations to be able to use the same apparent address to the client, but spread it again across multiple machines. And obviously this is how things like the root servers and the TLDs survive the kind of normal abuse, because they have to deal with millions of queries per second just with normal traffic. And the reality is those 13 root servers are actually each clusters of 20 to 50 physical sites, which might each have a half dozen machines all hiding behind that one single apparent A record. And obviously you can throw hardware at it. There are vendors who have high availability solutions to let you get more juice out of your hardware. So that's sort of the how do you defend your legitimate use of DNS on your side from the bad guys actually attacking your DNS. But as I said at the beginning, bad guys are not just sticking to taking your DNS out or trying to corrupt your DNS resolution. They are actually using DNS because DNS is a highly scalable distributed database, allows you to use an abstraction, a string, and have it go to multiple IP addresses, shuffling all of this stuff around. Zone transfers are a very efficient means if you're using IXFR to do essentially deltas of your database. And they've noticed that that works pretty well for a lot of things. So one of the biggest things that you see is an awful lot of the botnets have sort of tiered structure, much like you have a point-to-point file sharing network. All of the infected clients go up to some number of machines that sort of tell them what to do, but they actually report back to usually 1 or 2 clusters of command and control machines that actually have the latest code to get so that when you get infected, you stay infected. And when the virus scanner finally notices that you're infected with one thing, probably by that point in time, you're already running yet another piece of code on your machine. And the way that they do all of that is they hard code a domain name or an algorithmically derived domain name, and they know the algorithm, so they register domain names just in time, so you know that on this particular time, on this particular day, for a half an hour, this is the new domain name, and that's who you ask for your instructions. And they can change the IP address all the time to some address that the security vendors haven't found quite yet, and hopefully escape detection. Configure and Storm and some of the others have used that to hide One of the other things that they are using is what's called fast flux. That's where they have that DNS name, and that DNS name changes IP addresses really, really fast, which is why ACLs-based defenses become mostly useless to anyone doing fast flux. Because by the time you update your ACLs, which is probably a semi-manual process, they've already changed the IP address in that file, and they're going off and using a different one or connecting to a different machine already. Double flux is simply the idea that I don't have to just change the A record of this DNS label. I can have multiple A records for that label, and I can change all of them and intermingle them to make it even harder. It's the ultimate game of whack-a-mole. So what do you do when you're looking at all of this? Well, obviously you need to be able to protect yourself at varying points in time. One of the other things that most of us are dealing with these days is that marketing beaten to death phrase, bring your own device. But the reality is that 5 years ago, my company gave me a laptop. And if I didn't like that laptop, I pretty much got to buy my own, but I couldn't use it at work, or I left and went to another company. These days, companies are even encouraging their users to buy their own laptops because it saves them money. You become your own IT staff, which means that all of your sales guys and all of your marketing folks and all of your accounting and admin people are your security and IT experts, which should make you nervous if it doesn't. And they also have phones and they have tablets. And I can pretty much guarantee almost nobody here had their company buy it for them. But most companies don't prohibit you from bringing it into the office. And that means that you have a potentially multi-user, multi-process, general purpose operating system running on your internal network with no idea of what the patch levels are. It's not even like Windows where, yes, you can bring in your own machine and we can still group policy it, and when you log in with your AD, we have some control. Or Mac where, unless they're smart enough to turn off auto update, you at least know they will be getting the latest and greatest from Apple, for better or worse. Phones are different. Phone companies selling phones don't like you on the latest version of Android because your phone is 2 years old, and they like you on the 2-year-old version of Android, because then when you complain that it sucks and you want to upgrade it, they say, well, we're really, really sorry that the version 1 phone will not run with this version of Android, but if you'd like to re-up your contract, we will happily sell you the new phone. So the reality is that you have lots of people running around with 2-year-old code. And that's another, in the world where there are thousands of new viruses coming out per day in variations. And that's on PCs for which there is antivirus for some level of effectiveness. Many of your devices don't even have the option of running some form of virusware. So, what can you do to try and protect your network and your users? Well, obviously, wherever you can, use antivirus. There are a number of people that will be very happy to sell you boxes, next generation firewalls that claim to be clever, stateful packet inspection, intrusion detection, advanced persistent threat analysis, and every other latest acronym that they have come up with to tell you that they know better than you what's going on in your network and what's going to work. And it works about as well as most of us expect from our vendors. There are places where, in theory, you can finally actually use DNS, and I'll talk about that. So, a little bit more on where these go. Antivirus. Antivirus can be effective, and it does block things. And one of the sort of watchwords of security is a belt is good, belt and suspenders is even better. The more things you can put in place to catch at least something, the more chances you are that the thing that your user brought in might get prevented. It's a good theory. There are some issues, obviously. One of them is it's tunable on how often you can get new updates or how often updates are available from your vendor. I remember in the old days at Symantec, most corporations would check once a week. The more paranoid places would check once a day. 2 years ago, I remember telling clients that if you aren't getting new virus updates every 15 minutes, you will be infected by lunch. And I suspect it's worse now. I have not been doing as much direct security work. So obviously, it depends on what the vendor has and how good the software is, and if there is software. Apple puts out updates once every month, every 2 months, every 3 months, unless it's an absolutely hideous, totally broken security hole, in which case, like Java, it only took them, a couple weeks after it was announced. Microsoft has their own these days if you're running modern, but quick show of hands, is there anyone here still supporting XP? Wow. Okay, couple, yeah. Even though Microsoft, in theory, is no longer supporting XP, if you're paying enough money, they are still supporting XP. And the new virus stuff started coming out in Windows 7 and Vista, and has been improved somewhat. There are obviously plenty of commercial products for that. Haven't seen much in the way of useful stuff for phones or tablets yet. There are several vendors that are, of course, claiming that they have things. Most don't seem to be overly useful. Bottom line is that viruses are too easy to change and too hard to predict to have this as your only protection anymore. There are too many places that things can come in now. And even if you have virus protection, even if it's working, and even if it's fairly timely, in most cases it's not very hard once you've infected a machine to disable firewall protections and virus checking and make the system think it's still on. Most of the better rootkit stuff I've seen, once you're infected, because your virus definitions were just a bit too old, usually you're pretty much owned. And you are owned until you wipe back to a clean OS, restore your user files, and hope that that wasn't where it was living. Perimeter defenses are where you can use them much more effective. Obviously, if it is something where it's an IP address range where you can actually filter, beautiful. Certainly do that. And there are people who certainly filter by policy. I am pretty sure that it is actually required by the government agencies to block certain ranges of ASs completely relating to China. They don't even care what they are missing. They are far more concerned with those folks getting in. Okay? You know, sadly, of course, these guys wind up popping through other places anyway, so it's another of the, it's a pretty thin layer, but it is another layer. But one of the problems, of course, with catching things that are perimeter is, you know, if you have a hard and crunchy outer shell and a soft and gooey center, and a user can insert things right into the gooey center, doesn't matter what your hard and crunchy outer shell is. You've already lost, and everybody else that comes into that soft and gooey center doesn't have any protection from that person who came in. So again, the story of somebody whose kid downloaded a cool screensaver or some new game and wound up infecting your PC or your tablet or your phone, and they bring it in, they dump it on your network. Everyone else, at least on that network, is at risk. So usually you can only detect that they are infected once the malware that's in there tries to connect to a command and control system to check in or to download new code. And again, you can only detect that if you know that it's a bad address to prevent it, or when the file is coming back in, you inspect the file download and go, wait a minute, that's really not good code. I'm going to prevent the user from actually getting it. There are some issues with that as well. Most of the reputation-based lists of these are known bad people, are done in retrospect based on people who've already been attacked. and they're usually in IP addresses. Very seldom do you get domain names, because most of the time the bad guys are registering a domain name is cheap. You know, $12 for 10 or 15 minutes of unfettered use with an algorithmically derived domain name that I know won't be taken before I register it, and then I throw it away because it's already bad. That's cheap to those guys with the amount of money they make. The other problem with most of the perimeter devices is you don't have external feeds of information. Most of the information you get is based on learning from what it's seen in that environment or from that vendor's own customers only. So it's a somewhat closed and artificial system. There are some that are better than others, and that's one of the things you should check when you are shopping, is how wide and varied is their source of reputation data. But in most cases, it's pretty static, and updates are in terms of usually hours, not minutes. There is something called RPZ, Response Policy Zones, where it's a special DNS zone. And you get a feed which gives you the reputation of bad people. And the nice thing is that you can put IP addresses or domain names into that list. It can be updated very rapidly because you can actually use DNS's own file transfer methods, including IXFR, incremental zone transfers, to give me just the deltas. So once you've gotten the initial load of that RPZ zone, you have just got deltas to change. And because it is DNS, it uses the notify cycle. So as soon as your reputation feed sticks in new data, you are immediately told. And you can then go off and query and get that IXFR in more or less real time. And there are sources of these feeds that are commercial products where they are getting data from 20 and 30 and 40 different complete areas and blocks, including honeypots and other things that deliberately attract bad people so they can watch the traffic silently and passively so they can feed that into there so you get it. Other nice thing is, because it's DNS, it gets triggered when the client makes the DNS query. If I query either a domain name that hits that list, so my recursive server has this zone in it. And so when I as a client make the query, my recursive server will look and it will say, gee, that domain is known to be bad. I've caught it immediately. Or it will do the query and it will notice that one of the name servers listed or the A record IP address resolves into something that's in that list. So I have multiple ways or chances to catch it, including things like this set of name servers is known bad, so any domain that asks for it that has these name servers, even though the IP address I asked for isn't in the list, and even though the domain name I asked for isn't in the list, the fact that the auth servers for that domain are in the list is enough to tell me that's probably another bad domain. And in all cases, I get it at the point at which the client has just started to ask as the first step. So I can do all sorts of things. I can say NX domain. I can give them a false one, which gets them to a page. I can do other things immediately with it. I can start things like notice, reconfigure a switch, turn off a port. I can set up logging. I can do all sorts of things at the moment at which that client is infected and starts. So I don't have to worry about where or when the client got infected. I can be confident that at the point at which he makes the query, I notice. And depending on whose RPZ feed and which company's product, you may be able to track that down to exactly the client, the IP address, the MAC address, and possibly even if it's in some kind of IPAM system that has all this data, may very well have the guy's name, phone number, and desk. And you get it immediately at the point, the first time that machine tries to get to someplace bad. So all of these things have flaws. You know, obviously the RPZ feed, you need to be current, and if it's really new and it isn't in anybody's RPZ feed yet, you don't get that protection yet. If you don't know the IP address, your perimeter devices may not stop it, but there are an awful lot of things. RPZ won't catch somebody who's not in the list yet, but your perimeter device will catch that file as it's downloading and go, wait a minute, that's malware. So again, belt and suspenders. Use every possible device that you can to go through. So, do I have any questions?
Is there a question?
I've got one. You've talked about the RPZs and that there are commercial solutions working with it. Could you please provide an example of an open source solution?
Well, the open source solution for RPZ, both NSD/Unbound and Bind from ISC will use RPZ. So if you have an Unbound resolver or a Bind resolver, they will be able to use the RPZ. What you do with that information is sort of where you get the value add, or you're going to have to roll your own. With a commercial product, obviously, that's the point at which you might have an IP address management system that can pull more data other than the fact that somebody asked for it. All you know with DNS is essentially the source port of the UDP packet making the initial request. But there's nothing stopping you also from, if you have your own IPAM system or you have your own DHCP system that keeps track of all of that stuff, yeah, you can certainly roll your own. And the feeds are compatible with any of them because it is a DNS zone and it is now a published standard.
Any other questions?
All right, thank you very much.
Thank you very much.